Look up at the night sky. See those stars? Every telescope image you've ever seen? Every cosmic photograph NASA has released? Here's something that's going to fundamentally break your brain. We haven't seen 95% of the universe. Not because our telescopes aren't powerful enough. Not because we haven't looked hard enough. But because that 95% is literally invisible. It doesn't interact with light. It doesn't emit radiation. And yet, without it, you wouldn't exist. But here's where it gets absolutely insane. What if I told you that even that number to 95% is wrong? What if the universe we can't see is actually far, far larger than we thought? What if everything we've been teaching in physics classes, everything in your textbooks, every documentary you've watched, has been based on a fundamental miscalculation? In the next 3.5 hours, I'm going to take you on a journey that will completely reshape how you understand reality itself. We're going to explore why the greatest minds in physics are now questioning whether we've been catastrophically wrong about the size, age, and nature of the cosmos. And by the end, you're going to see yourself, your life, and your place in existence in a way you never imagined possible. Before we dive into this mind-bending journey, do me a favor. Smash that like button right now, because what you're about to learn isn't taught in schools, and this video needs to reach as many curious minds as possible. Hit subscribe and turn on notifications, because we're going deep into the cutting edge of cosmology. And drop a comment right now telling me, what country are you watching from, and what time is it where you are? I want to know how far across this globe, this tiny speck in an incomprehensibly vast universe, this message is reaching. Are you watching at midnight in Tokyo? During lunch in Brazil? On your morning commute in London? Let me know. Let's start with what you think you know about the universe. You've probably heard that the universe is about 13.8 billion years old. You've probably been told that when we look through telescopes, we can see back to almost the beginning of time. You might even know that the observable universe is about 93 billion light years across, bigger than 13.8 billion light years, because space itself has been expanding. These numbers get thrown around like they're settled science, like we've got this figured out. But here's your first revelation. Every single one of these numbers is based on what we can see. And what we can see represents such a monumentally tiny fraction of what exists that it's like trying to understand the entire Pacific Ocean by examining a single drop of water under a microscope. Let me paint you a picture. Imagine you're standing in a massive library, the library of everything. This library contains every piece of information about the universe. Every particle, every force, every dimension, every moment in time. Now imagine that this library has 10,000 floors, each floor stretching for miles in every direction, packed with books. You walk in, and you're given access to exactly half of one shelf on the ground floor. Not even half, more like 5% of one shelf. That's where we are. That's what we've seen of the universe. But it gets stranger, much stranger. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a collection of over 1,000 galaxies bound together by gravity. He did something simple. He calculated how fast these galaxies were moving and how much mass they should have based on the light they emitted. Then he calculated how much mass they would need to stay gravitationally bound at those speeds. The numbers didn't match. Not even close. The galaxies were moving so fast that based on their visible mass, they should have torn the cluster apart millions of years ago. But they hadn't. Something invisible, something that didn't emit, absorb or reflect light, was holding them together. Zwicky called it dunkel materie, dark matter. For decades, physicists dismissed him. It seemed absurd. How could there be matter we couldn't see? Matter that didn't interact with light at all. Then, in the 1970s, astronomer Vera Rubin made an observation that would change everything. She was studying spiral galaxies, measuring how fast stars orbited around their centers. According to Newton's laws and everything we understood about gravity, stars farther from the galactic center should orbit slower, just like planets farther from our sun take longer to complete their orbits. But that's not what she found. Stars on the outer edges of galaxies were moving just as fast as stars near the center. It was as if there was a massive halo of invisible matter surrounding every galaxy, providing extra gravitational pull to keep those outer stars moving faster than they should. The evidence became overwhelming. Dark matter had to exist. And when physicists calculated how much of it there must be, the number was staggering. About 27% of the entire universe is made of this invisible substance. Everything we can see, every star, every planet, every galaxy, makes up less than 5% of the total mass and energy in the cosmos. Think about that. Everything humanity has ever observed, photographed, or studied represents less than 1/20th of what's actually out there. But wait, it gets worse. Here's where your brain is about to break. Dark matter isn't even the weirdest part. At least with dark matter, we understand how it behaves. It has gravity. It clumps together. It forms the scaffolding that allowed galaxies to form in the first place. Without dark matter, you literally wouldn't exist. There would be no galaxies, no stars, no planets, no life. But in 1998, two teams of astronomers, one led by Saul Perlmutter, the other by Adam Rees and Brian Schmidt, made a discovery so shocking, so counterintuitive, that even they didn't believe their own results at first. They won the Nobel Prize for it in 2011. They were studying distant supernova, exploding stars that act as cosmic measuring sticks because they always explode with roughly the same brightness. By measuring how bright these supernova appeared from Earth and comparing that to how bright they should be, the teams could calculate how far away they were. And by measuring their redshift, how much their light had been stretched by the expansion of space, they could figure out how fast they were moving away from us. Everyone expected to find that the universe's expansion was slowing down. After all, gravity should be pulling everything back together, right? Even if there wasn't enough matter to completely halt the expansion and cause a big crunch, gravity should at least be putting the brakes on. But that's not what they found. Not at all. The universe's expansion was accelerating, speeding up, as if some mysterious force was pushing space itself apart, overwhelming gravity's pull. They called this force dark energy. And when physicists calculated how much dark energy there must be to account for this acceleration, the number was mind-blowing. Approximately 68% of the entire universe. Let me break this down for you. Of everything in the universe, 68% is dark energy, a mysterious force pushing space apart. 27% is dark matter, invisible matter we can only detect through gravity. 5% is ordinary matter, the stuff we can actually see and touch. We've been exploring less than 5% of reality. Everything else? Complete mystery. Now you might be thinking, okay, so there's invisible stuff out there, but we can still see pretty far, right? Those deep space telescope images show us galaxies billions of light years away. We can see back to almost the Big Bang. Here's what's going to mess with your head. Even within that 5% of ordinary matter, we can only observe a tiny bubble around us. And the edge of that bubble isn't determined by the power of our telescopes. It's determined by the age of the universe itself and the speed of light. Think of it like this. You're standing in the middle of an infinitely large, pitch-black room. You turn on a flashlight. The beam extends outward, illuminating everything in its path. But there's a limit to how far that light has traveled since you turned on the flashlight. Beyond that limit? Darkness. Not because there's nothing there, but because the light hasn't had time to reach you yet. That's the observable universe. It's a sphere centered on Earth, with a radius of about 46.5 billion light years. That's how far light has been able to travel since the Big Bang, accounting for the expansion of space. But here's the kicker. The universe doesn't end at the edge of our observable bubble. There's no cosmic wall out there with a sign saying, universe ends here. The universe keeps going. There are galaxies beyond our observable horizon, and galaxies beyond those galaxies, and galaxies beyond those. How much further does it go? We don't know. It might be infinite. It might be finite, but so large that infinity is the closest word we have. Some calculations suggest the entire universe could be at least 250 times larger than the observable universe. Others suggest it could be vastly bigger than that, or infinite. Everything we've ever studied, everything in every astronomy textbook, represents one tiny bubble in an ocean we can't even begin to measure. But it gets even more mind-bending. That edge of the observable universe? It's not the same for everyone. An alien civilization in a galaxy 10 billion light-years from Earth would have their own observable universe, their own bubble centered on them. Their bubble would overlap with ours, but it would also extend into regions we can never see, revealing galaxies and structures that are, from our perspective, beyond the horizon of observable reality. And here's where it gets really trippy. There are parts of the universe that are receding from us faster than the speed of light. Not because anything is moving through space faster than light. That's still impossible, according to Einstein's relativity. But because space itself is expanding, and that expansion is accelerating. Right now, there are galaxies so far away that even though their light has been traveling toward us for billions of years, they're moving away from us faster than their light can approach. We'll never see them. Ever. The universe's expansion is carrying them away faster than light can close the gap. In fact, the observable universe is shrinking in a sense. Not in physical size, it's actually getting larger as more light reaches us from previously distant objects. But in terms of the fraction of the total universe we can potentially observe, we're seeing less and less over time. Galaxies that are currently visible to us will eventually disappear beyond the cosmic horizon, their light redshifted into oblivion. Future civilizations, billions of years from now, will look up at a much emptier sky. If there are alien astronomers in the far future, they might conclude they live in an isolated island universe, surrounded by nothing but dark, expanding space. They'd be wrong. Of course, there would still be countless galaxies out there, but they'd never be able to see them or know they exist. Now let me absolutely blow your mind with something most people don't realize. We can't even see back to the actual Big Bang. You've probably heard about the cosmic microwave background, the CMB. It's often called the baby picture of the universe. Radiation left over from 380,000 years after the Big Bang. When space telescopes map the CMB, they create these beautiful, colorful images showing temperature variations across the early universe. This is the furthest back we can see with light. Not because there wasn't anything before that, but because before that moment, the universe was opaque. Picture this. In the first 380,000 years after the Big Bang, the universe was so hot and dense that it was essentially a fog of plasma, a soup of electrons and protons so thick that light couldn't travel through it. Photons would bounce off electrons almost immediately, like trying to shine a flashlight through a thick cloud. Then, 380,000 years in, the universe had expanded and cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, photons could travel freely. The fog cleared. That first light, the moment the universe became transparent, is what we see as the cosmic microwave background. But everything before that? Hidden. Invisible. Not just invisible to our current technology, but fundamentally invisible to any form of light-based observation, no matter how advanced our telescopes become. Those first 380,000 years, a critical period that includes the Big Bang itself and the earliest moments of cosmic evolution, are hidden behind an impenetrable wall. We're like detectives trying to solve a crime, but the first chapter of the case file has been redacted, and no amount of technology can unredact it. We can infer what happened. We can build mathematical models. We can use indirect evidence. but we cannot see it. That part of the universe's history is forever beyond the reach of telescopes. Okay, but here's where it gets interesting. Physicists aren't giving up. They realized something clever. We can't see the early universe with light, but light isn't the only way to observe the cosmos. Think of it like this. Imagine you're standing outside a house at night, trying to figure out what's happening inside. The curtains are drawn, so you can't see through the windows. That's like trying to observe the early universe with light. The plasma fog blocks your view. But you could hear what's inside. Sound waves pass through walls. You could feel vibrations. You could detect heat. There are other ways to gather information besides light. The same is true for the universe. And scientists are now building detectors for two types of cosmic messengers that can penetrate that early fog: neutrinos and gravitational waves. Neutrinos are ghost-like particles that barely interact with anything. Trillions pass through your body every second without you noticing. They were created in the first seconds after the Big Bang, and they've been streaming through the universe ever since, passing through the plasma fog like it wasn't even there. If we could build detectors sensitive enough to catch these primordial neutrinos, the cosmic neutrino background, we could see back to just 1 second after the Big Bang. 1 second. Compare that to the 380,000 years the CMB shows us. And gravitational waves, ripples in spacetime itself, detected for the first time in 2015 by LIGO, could potentially let us observe back to a tiny fraction of a second after the Big Bang. Some physicists think we might eventually detect primordial gravitational waves from the Big Bang itself. These technologies are still in their infancy, but they represent a new way of seeing the universe, not with light, but with entirely different cosmic messengers. We're learning that seeing is just one narrow slice of observation. Reality reveals itself in multiple ways, if we're clever enough to listen. Now, everything I've told you so far assumes we're talking about one universe. Our universe. The universe that started with the Big Bang 13.8 billion years ago and has been expanding ever since. But what if even that assumption is wrong? What if our universe, everything within our cosmic horizon, everything that emerged from our Big Bang, is just one bubble in an infinitely larger structure? What if there are other universes, separate from ours, with their own Big Bangs, their own physical laws, their own histories? This isn't science fiction. This is serious theoretical physics, being explored by researchers at institutions like MIT, Stanford, and Cambridge. The idea is called the multiverse, and while it's controversial, several well-established theories in physics naturally lead to it. Let me explain one version: eternal inflation. In the 1980s, physicist Alan Guth proposed inflation theory to solve some problems with the standard Big Bang model. The idea is that in the first fraction of a second after the Big Bang, we're talking 10 to 32 seconds, space expanded exponentially fast, faster than the speed of light. In less time than it takes light to cross a single proton, the universe expanded from smaller than an atom to potentially larger than the observable universe is today. This solves several problems in cosmology. But here's where it gets wild. When physicists ran the math, they realized that inflation, once started, might never fully stop. In most regions of space, inflation ends and you get a universe like ours: matter, galaxies, stars, planets. But in other regions, space keeps inflating, and occasionally, new bubble universes form within that inflating space. Our Big Bang wouldn't be the beginning of everything. It would be the moment inflation stopped in our local bubble, allowing matter and energy to form. But beyond our bubble, there could be countless other bubbles, each one a separate universe with its own Big Bang, its own expansion, maybe even its own physical constants. If eternal inflation is correct, then everything we call the universe is actually just one tiny region in an infinitely large multiverse. The distance to these other universes? Potentially infinite. The number of them? potentially infinite. How much of reality have we seen? Not 5%, not 0.0000%. We might have seen an infinitely small fraction of what exists. But wait, there's another possibility that's even more mind-bending. What if the universe we see isn't just one bubble among many, but one cycle in an eternal process of birth, death, and rebirth? This is the cyclic universe model, and it completely appends the idea that the Big Bang was the beginning of time. Here's the concept. Imagine the universe is like a bouncing ball. It expands from a Big Bang, reaches a maximum size, then contracts back down in a big crunch. But instead of collapsing into a singularity and ending, it bounces, triggering another Big Bang, another expansion, another universe. This cycle might have been happening forever. Our Big Bang, 13.8 billion years ago, might have been preceded by another universe, which was preceded by another, stretching back infinitely into the past. Some versions of this theory involve something called brain cosmology. Imagine our universe is a three-dimensional membrane, a brain, floating in a higher dimensional space. There might be other brains nearby, also floating in this higher dimensional void. Occasionally, these brains collide. When they do, the energy released triggers a Big Bang on both brains, creating or renewing universes. Under this model, what we call the Big Bang wasn't the beginning of time or space. It was just a collision, one of countless collisions that have occurred and will occur across eternity. How much of reality have we seen? If the universe is cyclic, we've seen one phase of one cycle. The previous universes? Gone, leaving almost no trace. The future universes? Not yet born. We're observing a single frame in an infinite movie. Now, I want to take you somewhere really strange. Let's talk about whether the universe we observe is even real in the sense we think it is. In 2003, philosopher Nick Bostrom published a paper proposing the simulation hypothesis. His argument goes like this. If it's possible for a civilization to create simulated universes, detailed, conscious mind-containing simulations, then statistically, we're almost certainly living in one. Why? Because if even one civilization in the real universe reaches the point where it can run millions or billions of simulated universes, then the number of simulated universes vastly outnumbers the one real universe. If you're a conscious being, you're more likely to be in one of the trillions of simulations than in the single original reality. This sounds like philosophy, not physics, but some physicists take it seriously. Why? Because when we examine the universe at its deepest levels, it starts to look suspiciously like a simulation. Consider quantum mechanics. At the smallest scales, reality appears pixelated. There's a smallest possible unit of length, the Planck length, about 10 to 35 meters. There's a smallest unit of time, the Planck time. There's a fundamental graininess to reality, like the pixels on a computer screen. Then there's the way quantum mechanics works. Particles don't have definite properties until they're observed. It's as if the universe is saving computational resources by not rendering details until something looks at them. Exactly what a video game does. The part of the game world you're not looking at exists in a lower resolution state until you turn around and look at it. And the speed of light, the ultimate speed limit of the universe? In a simulation, that would be the maximum processing speed, the rate at which information can propagate through the system. I'm not saying we definitely live in a simulation. The hypothesis is unfalsifiable. There's no way to prove we're not in a simulation, since any evidence we found could itself be part of the simulation. But it raises a profound question. If we are in a simulation, how much of the universe we observe actually exists? The simulator might only render the parts we can observe. Everything beyond our cosmic horizon? It might not actually exist in any meaningful sense. It might be placeholder data, only brought into existence if and when it becomes observable. How much have we seen? If we're in a simulation, we might have seen everything that's been rendered. But the underlying reality? That could be something entirely different, existing on a scale and in dimensions we can't begin to imagine. Okay, let's step back from the philosophical edge and return to observational science. Because there's a piece of evidence that challenges everything we think we know about the size and structure of the universe, and it was discovered entirely by accident. In the 1970s and 80s, astronomers started mapping the positions of galaxies in three-dimensional space. They expected to find galaxies more or less randomly distributed, maybe with some clumping here and there. What they found instead was structure, vast structure. Galaxies weren't scattered randomly. They were organized into enormous filaments, sheets, and walls, separated by vast voids where almost no galaxies existed. The universe looked like a cosmic web, a foam-like structure with galaxies concentrated on the bubble surfaces and emptiness inside the bubbles. And these structures were huge. The Sloan Great Wall, discovered in 2003, is a massive filament of galaxies stretching across 1.37 billion light-years. The Hercules Corona Borealis Great Wall, discovered in 2013, is even larger, about 10 billion light-years across. That's roughly 1/10 the diameter of the observable universe. Here's the problem. According to our current understanding of cosmology, structures this large shouldn't exist. The universe hasn't been around long enough for gravity to pull together structures spanning billions of light-years. Let me explain. After the Big Bang, matter was distributed almost uniformly, with tiny variations in density, the seeds that would eventually grow into galaxies and galaxy clusters through gravitational attraction. But gravity works relatively slowly. It takes time for these seeds to grow. When physicists calculate the maximum size of structures that could have formed in 13.8 billion years, they get a number around 1.2 billion light-years. Yet we observe structures significantly larger than that. What does this mean? Either our understanding of how cosmic structures form is wrong, or these structures are evidence of something deeper, perhaps patterns in the initial conditions of the universe that we don't yet understand, or perhaps evidence that the universe is older or stranger than we think. Some cosmologists have proposed that these structures might be imprints of pre-Big Bang physics, patterns inherited from whatever existed before our universe began. Others suggest they might be evidence of cosmic inflation, frozen to the fabric of space during that first explosive moment. But here's what really matters. We've been studying the universe for centuries, using increasingly powerful telescopes, and we keep finding structures larger than we thought possible. Every time we think we've found the largest structures in the cosmos, we look deeper and find something bigger. What does this tell us? That we fundamentally don't understand the scale at which the universe operates. We're like ants discovering that the patch of ground we've been exploring is actually part of a garden, which is part of a neighborhood, which is part of a city, which is part of a country, which is part of a planet. Now let me tell you about something even weirder. Something that suggests our entire observable universe, that 93 billion light-year bubble we call home, might be moving through space as a single unit, pulled by something enormous that exists beyond what we can see. In 2008, NASA's Wilkinson Microwave Anisotropy Probe was studying the cosmic microwave background, that baby picture of the universe I mentioned earlier. A team led by Alexander Koshlinsky noticed something strange. Galaxy clusters weren't just moving in random directions. They were flowing as a group in one particular direction. This phenomenon was called dark flow, and it's traveling at about 600 kilometers per second in the direction of the constellations Centaurus and Hydra. Now, 600 kilometers per second might not sound fast, but remember, galaxy clusters are enormous structures, each containing hundreds or thousands of galaxies. For entire clusters to be moving in the same direction, something with colossal gravitational pull must be attracting them. But here's the thing, there's nothing in that direction. At least, nothing we can see within our observable universe. The source of the pull appears to be beyond our cosmic horizon. Let me give you an analogy. Imagine you're in a boat on a river, but the river is covered in thick fog. You can only see about 100 meters in any direction. You notice that your boat, and all the other boats around you, are drifting in one particular direction. Something is pulling the water, and you along with it. But the source of that pull is beyond the fog. You can't see what's causing it, but you know something massive must be out there. That's dark flow. Our entire observable universe might be drifting towards some massive structure, perhaps an enormous concentration of matter, or even another universe that exists beyond what we can possibly observe. If dark flow is real, and I should mention it's controversial, some studies have confirmed it, others haven't found evidence for it, then it means our observable universe isn't a static, isolated bubble. We're moving. We're being pulled. And the thing doing the pulling is so far away and so massive that it makes everything we've ever observed look tiny by comparison. How much of the universe have we seen? If dark flow is real, then whatever's pulling us is larger than everything in our observable universe combined. And it's entirely invisible to us, lurking beyond the horizon like some cosmic leviathan. While we're on the topic of mysterious patterns in the cosmic microwave background, let me tell you about something cosmologists have nicknamed the axis of evil. And no, that's not melodrama. That's actually what they call it. When scientists first mapped the CMB in detail, using satellites like COBE, WMAP, and Planck, they expected to see temperature variations that were essentially random, tiny hot and cold spots scattered uniformly across the sky, representing the quantum fluctuations in the early universe that would eventually grow into galaxies. What they found instead was disturbing. The largest scale temperature variations, the biggest hot and cold spots in the baby picture of the universe, weren't randomly distributed. They appeared to be aligned with each other, creating an axis through space. Even weirder, this axis seemed to align with the plane of Earth's solar system and the equinox. This should be impossible. The CMB is showing us the universe as it existed 380,000 years after the Big Bang, 13.8 billion years ago. There's no reason its patterns should have any relationship whatsoever to Earth's location or orientation in space. That would be like finding your phone number encoded in the pattern of craters on the moon. It's too much of a coincidence to be random. Several explanations have been proposed. Maybe it's an artifact of how we process the data. Maybe it's contamination from our own galaxy's radiation. Maybe there's a systematic error in our instruments. Or maybe, and this is the disturbing possibility, it's real. Maybe the universe has a preferred direction or orientation. Maybe the cosmological principle, which states that the universe should look the same in all directions, is wrong. Maybe we're not living in a uniform, isotropic cosmos, but in something stranger, something with structure and orientation on scales vastly larger than anything we've conceived of. If the axis of evil is real, it means the universe we observe is embedded in or influenced by something much larger. Like finding out your house isn't just sitting on land, but is part of a pattern, part of a design so large you can only see it from space. Some researchers have suggested this could be evidence of a collision between our universe and another in the early moments after the Big Bang, a bruise left on our cosmic bubble by an encounter with a neighboring bubble. Others think it might be evidence of higher dimensional structure, something existing in dimensions we can't directly perceive, but which influences the 3 dimensions we inhabit. Whatever it is, it's evidence that we're missing something fundamental about the universe's structure. Something big. Now I want to talk about a crisis that's currently shaking cosmology to its core. It's called the Hubble tension, and it might mean that everything we think we know about the universe's expansion is wrong. Here's the setup. The Hubble constant is a number that tells us how fast the universe is expanding. It's measured in kilometers per second, per megaparsec. Essentially, how much faster a galaxy appears to be moving away from us for every million parsecs of distance. For decades, astronomers have been trying to pin down the exact value of this constant. And here's where things get weird. Depending on how you measure it, you get different answers. When you measure the Hubble constant using the cosmic microwave background, looking at the early universe and extrapolating forward, you get a value, around 67 kilometers per second, MPC. This measurement was made with incredible precision by the Planck satellite. But when you measure it using local observations, looking at nearby supernova, Cepheid variable stars, and other standard candles, you get a value around 73 kilometers per second, MPC. This was measured by Adam Rees's team using the Hubble Space Telescope. That's a 9% difference. That might not sound like much, but in cosmology, it's enormous. Both measurements have been checked and rechecked. Both teams are confident in their results. And yet they disagree. This isn't a matter of experimental error. The discrepancy is too large and too consistent. One of three things must be true. 1. There's some systematic error we haven't identified in how we measure cosmic distances. 2. Our understanding of how the universe evolved is incomplete or wrong. 3. Something fundamentally weird is happening with the fabric of space and time. Here's why this matters for our discussion. If option 2 or 3 is correct, then our entire model of the universe's expansion might be wrong. The age of the universe might be different than we think. The size of the observable universe might be different. The amount of dark energy might be different. Some physicists have proposed exotic solutions. Maybe dark energy isn't constant. Maybe it's changing over time, evolving in ways we haven't accounted for. Maybe there are extra particles or fields we haven't detected that influence the early universe. Maybe the universe isn't expanding uniformly. Maybe it's expanding at different rates in different directions. Or maybe, and this is the most radical possibility, the laws of physics themselves have changed over cosmic time. The physical constants we think are constant might actually be variables. If any of these explanations are correct, then the universe we think we're observing might be significantly different from the universe that actually exists. We might have fundamentally miscalculated how much of reality we're seeing. Let me tie together everything we've discussed so far, because I want to make sure you understand just how profound this is. We started by learning that 95% of the universe, dark matter and dark energy, is invisible to our telescopes. Then we learned that even the 5% we can see is limited by cosmic horizons, and that the total universe might be hundreds or thousands of times larger than what we can observe. Then we discovered that cosmological theories like eternal inflation and cyclic universes suggest our Big Bang might be just one event among countless others, making the true scope of reality potentially infinite. Then things got even stranger. We found evidence of massive structures that shouldn't exist, of mysterious flows that suggest our entire observable universe is being pulled by something beyond our horizon, of patterns in the CMB that hint at higher dimensional or multi-universal influences. And now we're discovering that even our basic measurements of how the universe expands might be wrong. Here's what all of this means. We don't know how much of the universe we've seen. We might have observed 5% of the observable universe's mass energy. We might have observed far less than 0.0000001% of the total universe. Or if the multiverse exists, if reality is truly infinite, we might have observed an infinitely small fraction of what exists. But more importantly, we don't even know what we're measuring. The very tools and concepts we use to define universe and observation might be inadequate for the true scale and nature of reality. It's like asking an ant how much of Earth it has explored. Not only has it seen just a tiny patch of ground, but it lacks the conceptual framework to even understand what Earth means, that it's a sphere, that it's in space, that it's orbiting a star, that it's part of a galaxy. The ant can't conceive of the scale at which Earth exists. We might be in the same position. We're ants trying to understand reality, armed with mathematics and telescopes, discovering that every answer we find reveals 10 new questions, each one suggesting that the universe is stranger, larger, and more complex than we imagined. Before we continue deeper into this rabbit hole, I need you to do something. If this is blowing your mind, hit that like button right now. Share this video with someone who needs to have their perspective shattered. And drop a comment telling me, what's the most mind-blowing thing you've learned so far? I read every comment, and I want to know which revelation hit you the hardest. Because we're only halfway through, and we're about to go much, much deeper. Let's talk about something that most people assume is absolutely fundamental to reality: the laws of physics. You probably think these laws are the same everywhere, and have been the same forever. But what if they're not? What if the very fabric of physical law is different in parts of the universe we can't see? In 1937, physicist Paul Dirac proposed something radical. What if the fundamental constants of nature, things like the speed of light, the charge of an electron, the strength of gravity, aren't actually constant? What if they change over cosmic time? For decades, this was considered fringe speculation. But in recent years, astronomers have found hints that Dirac might have been onto something. In 2001, James Webb and his team at the University of New South Wales studied light from distant quasars, incredibly bright objects powered by supermassive black holes. When light from a quasar passes through intervening gas clouds, the atoms in those clouds absorb light at specific wavelengths determined by the fine structure constant, a number that relates to how strongly electromagnetic forces interact with charged particles. Webb's team measured these absorption lines in light that had been traveling for 10 billion years from when the universe was much younger. And they found something shocking. The fine structure constant appeared to be different back then. Not by much, only about 1 part in 100,000, but measurably different. If confirmed, this means the laws of physics have changed over cosmic history. The universe 10 billion years ago operated under slightly different rules than the universe today. Other studies have found hints that the fine structure constant might also vary in space, that it might have different values in different parts of the universe. Some regions might have stronger electromagnetic forces, while others have weaker forces. Now, these results are controversial, and not all scientists accept them. But if they're correct, the implications are staggering. Think about it. Everything we observe in distant galaxies, we interpret through the lens of physics as we know it here and now. We assume that when we look at a star 10 billion light years away, it's following the same physical laws as stars in our own galaxy. But if physical constants change over space and time, then we're misinterpreting what we see. The universe might be radically different from our observations suggest. And here's the kicker. If physical constants vary across space, then in regions of the universe beyond our observation, those constants might be completely different. There might be areas where gravity is stronger or weaker, where light travels at a different speed, where the fundamental forces are balanced in entirely different ways. In some of those regions, matter as we know it might not be able to exist. Stars might not form. Atoms might be unstable. In other regions, the laws might be conducive to forms of matter and structures we can't even imagine. Physics so different from ours that we wouldn't recognize it as physics at all. How much of the universe have we seen? We've seen the part where physics works one way, but the universe where physics works differently. That's invisible to us, not because it's far away, but because we literally don't know how to look for it. Our entire observational framework is built on assumptions about physical law that might only apply locally. Now I want to take you even deeper into the weirdness. Let's talk about information, not in the sense of data, but in the fundamental physical sense. Because there's a paradox at the heart of our universe that challenges everything we think we know about what exists and what can be observed. In the 1970s, Stephen Hawking discovered something shocking about black holes. He calculated that black holes should slowly evaporate, radiating energy in the form of what's now called Hawking radiation. Eventually, over vast timescales, a black hole would evaporate completely and disappear. Here's the problem. If you throw a book into a black hole, All the information in that book, every word, every letter, every pattern of atoms, falls into the black hole. If the black hole then evaporates, where does that information go? Does it vanish from the universe? According to quantum mechanics, information can never be destroyed. It can be scrambled, spread out, made practically unrecoverable, but it must exist somewhere. This is the black hole information paradox, and it's driven physicists crazy for 5 decades. Leonard Susskind and Gerard 't Hooft proposed a radical solution in the 1990s, the holographic principle. The idea is that all the information about what falls into a black hole isn't destroyed. Instead, it's encoded on the black hole's event horizon, the surface of no return. Even though the information fell into a 3-dimensional volume, it's preserved as a 2-dimensional hologram on the surface. But here's where it gets mind-bending. If this principle applies to black holes, it might apply to the entire universe. Think about it. We're limited by a cosmic horizon, a boundary beyond which we can't see. That boundary, like a black hole's event horizon, might encode information holographically. Everything in the observable universe, every particle, every force, every moment of history, might be a holographic projection from a 2-dimensional surface at the edge of space. In other words, the 3-dimensional universe you experience might not be fundamental. It might be a hologram, and the real information content of reality is written on a distant boundary in one less dimension. This isn't just philosophy. This is serious physics being explored by researchers at Princeton, Stanford, and other leading institutions. And it's supported by some of the math that comes out of string theory and quantum gravity. If the holographic principle is correct, then the question, how much of the universe have we seen, becomes almost meaningless. We're not looking at reality itself. We're looking at a projection. The underlying information is encoded elsewhere, in a form we don't have direct access to. It's like asking how much of a movie you've seen when all you've observed is the shadows it casts on a wall. You might have watched the whole shadow play, but you haven't seen the projector, the film, or the mechanism that creates the images. The reality behind what you observe is something entirely different. While we're diving into the quantum realm, let me tell you about something that suggests the universe is far more connected, far more unified than our everyday experience suggests. I'm talking about quantum entanglement, and its implications are so bizarre that Einstein called it spooky action at a distance. Here's what happens. When 2 particles become entangled, they form a single quantum system. If you measure one particle and find it has a particular property, say it's spinning clockwise, then instantly, faster than light could travel between them, the other particle will have the opposite property. It will be spinning counterclockwise. This has been tested countless times. It's not a theory. It's experimentally verified. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger won the Nobel Prize for their work confirming quantum entanglement. Now here's the strange part. These particles could be separated by any distance. One could be on Earth, the other on the far side of the galaxy, and they'd still be connected. The measurement of one instantly affects the other, with no signal traveling between them. How is this possible? The answer appears to be that space itself, the distance between the particles, isn't as fundamental as we think. At the quantum level, those particles aren't really separate. They're part of a single non-local quantum state. The appearance of separation is in some sense an illusion. Now scale this up. In the earliest moments after the Big Bang, all the matter and energy in the universe was compressed into a tiny region, smaller than an atom. At that scale, everything was entangled with everything else. As the universe expanded, those entanglements were stretched across space, but they were never completely broken. This means that, at the quantum level, every particle in your body is still connected to particles in distant galaxies. The universe isn't a collection of separate objects. It's a single, unified quantum system that appears fragmented only because we observe it at a particular scale. When we ask, how much of the universe have we observed? we might be asking the wrong question. The universe isn't a collection of separate pieces where we've seen some and not others. It's a unified whole. We've seen certain aspects of that whole, certain projections of it, but the underlying reality is interconnected in ways that transcend the boundaries of space and time. Some physicists, like Juan Maldacena, have even proposed that the very structure of space-time, the fabric of the universe itself, emerges from patterns of quantum entanglement. Space doesn't exist independently. It's woven from quantum connections between particles. If you could see reality at its deepest level, you wouldn't see particles in space. You'd see a web of relationships, a network of quantum information from which the illusion of space and separation emerges. What have we seen? We've seen the surface appearance of a universe that, underneath, is something far stranger, a unified quantum tapestry where distance and separation might be convenient fictions rather than fundamental truths. Now let me take you somewhere that's going to make you question your place in reality. We need to talk about the anthropic principle and what it tells us about observational bias. Here's a strange fact. The universe appears to be fine-tuned for life. And I don't mean that in a vague philosophical sense. I mean that the fundamental constants of physics, the strength of gravity, the mass of the electron, the expansion rate of the universe, and dozens of others are calibrated to within a hair's breadth of the values needed for stars, planets, and life to exist. Let me give you one example, the cosmological constant, which determines the strength of dark energy. If it were even slightly larger, say, just 0.000000000000001% higher, the universe would have expanded so fast that galaxies could never form. No galaxies means no stars, no planets, no life. We wouldn't exist. But if the cosmological constant were much smaller or negative, the universe would have collapsed back on itself in a big crunch before stars could form. Again, no life. The value is balanced on a knife's edge. Change it by 1 part in 10,120. That's a 1 followed by 120 zeros, and we don't exist. This fine-tuning exists for many other constants too. The strength of the strong nuclear force, the ratio of electron to proton mass, the density of matter in the early universe, all of them sit in narrow ranges that allow for complex chemistry and life. Now, there are 2 ways to interpret this. Option 1, we got incredibly lucky. The universe just happened to have exactly the right properties for us to exist, against odds so astronomical that they're essentially impossible. Option 2, there are countless universes, each with different physical constants. Most of them are sterile, dead, unable to support life. But in the rare universes where the constants happen to be right, life emerges. And obviously, we find ourselves in one of those rare universes because we couldn't exist in the others. This is the anthropic principle. It's not that the universe was designed for us. It's that we can only observe the type of universe capable of producing observers. Here's why this matters. If the multiverse exists, if there are countless bubble universes with different physical laws, then we're subject to a massive observational bias. We can only see and study universes like ours. The vast majority of universes where physics is different are forever beyond our reach, not because they're far away, but because we literally couldn't exist in them to observe them. It's like asking a fish to explore the universe. The fish can study the ocean in incredible detail. It can learn about currents, about marine life, about the chemistry of water. But the fish can never observe land or air or space because it can only exist in water. The fish's observations are fundamentally limited by the environment it needs to survive. We're the fish. We can only observe universes where the laws of physics allow for observers. The countless universes where physics is different, where there's no chemistry, no complexity, no life, are invisible to us, not because we lack the tools to see them, but because our very existence depends on being in a universe like this one. How much of reality have we observed? If the multiverse is real, we've observed one extraordinarily rare type of universe among countless others. We've seen the oasis, but we're blind to the desert. Now I want to slow down and make this personal. Because everything I've told you, the invisible 95% of the universe, the cosmic horizons, the multiverse, the possibility that physical laws themselves vary across reality, all of this has a profound impact on how you should think about yourself and your life. You are made of atoms forged in the cores of ancient stars. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was created in stellar furnaces billions of years ago, then scattered across space when those stars exploded as supernova. But here's what's remarkable. Those atoms could have been spread anywhere in the universe. They could have ended up in interstellar space, drifting forever in the void. They could have fallen into a black hole. They could have formed a barren asteroid orbiting a dead star. Instead, through a chain of coincidences spanning billions of years, those atoms came together on this planet, in this solar system, and assembled themselves into you, into a structure capable of consciousness, of thought, of looking up at the cosmos and trying to understand it. You are the universe observing itself. You are a way for the cosmos to know its own existence. Carl Sagan said this, and it's more profound than it sounds. Everything we've discussed, dark matter, dark energy, cosmic horizons, multiverses, all of it exists in relation to observers. Without something to observe it, to measure it, to think about it, reality is just quantum probability waves. You collapse those waves into actual experience. You bring the universe into focus. And here's the thing. We've talked about how little of the universe we've observed, how tiny and limited our perspective is. That's true in one sense. But in another sense, you, yes, you, the person listening to this, represent something extraordinary. The universe is mostly empty space, mostly dark, mostly cold. The vast majority of cosmic volume is sterile, uninhabitable, devoid of complexity. Stars make up less than 0.5% of the universe's mass. Planets are even rarer. And planets with life? We don't know how rare life is, but it might be astoundingly uncommon. You exist in one of the universe's vanishingly rare pockets of complexity, consciousness, and meaning. You're not just observing the universe from some random location. You're in one of the most interesting, most intricate, most information-rich parts of reality. Think about it. The human brain contains roughly 86 billion neurons, each connected to thousands of others, creating trillions of synaptic connections. The number of possible states your brain can be in is larger than the number of atoms in the observable universe. Your subjective experience, your thoughts, your memories, your consciousness is a pattern of information as complex and unique as any galaxy. When we say we've only observed 5% of the universe, we're talking about matter and energy. But there's another way to measure what we've seen. We can measure it in information, in complexity, in meaning. And by that measure, you, a conscious being, capable of understanding and wonder, are one of the most significant things in the universe. Not because you're physically large or powerful, but because you contain patterns of information, depths of experience, layers of meaning that dwarf the complexity of 1,000 lifeless galaxies. Let me make this even more specific. Let's talk about your own personal observable universe, not in the cosmic sense, but in the experiential sense. Everything you know about reality comes through your senses. Light hits your retinas, sound waves vibrate your eardrums, molecules trigger receptors in your nose and tongue, pressure activates nerves in your skin. That's it. Those are your only windows into the universe. And then your brain takes those signals and constructs what you experience as reality. It fills in gaps, makes assumptions, creates a coherent narrative from fragmentary data. When you look at a scene, you think you're seeing everything, but your eyes only have high-resolution vision in a tiny spot at the center of your visual field. Everything else is peripheral, low resolution, and heavily interpolated by your brain. In fact, you experience a slight delay. By the time your brain has processed sensory information and constructed your conscious experience, about 80 milliseconds have passed. You're always living slightly in the past, experiencing a reality your brain has rendered based on slightly outdated information. Here's my point. Just as we've only observed a tiny fraction of the cosmic universe, you've only directly experienced a tiny fraction of reality. Most of what you think you know is inference, interpretation, mental construction. You've never directly experienced an atom, even though you're made of trillions of them. You've never seen an electromagnetic wave, even though they're passing through you constantly. You've never witnessed a chemical reaction in your own neurons, even though millions happen every second to generate your thoughts. The reality you experience is a model, a useful one, an accurate enough for survival one, but still a model. Your brain creates a user interface for reality, showing you colors, shapes, sounds, textures. But those aren't what's really there at the deepest level. At the deepest level, there are quantum fields, probability waves, mathematical relationships. So when you hear that we've only observed 5% of the universe's matter and energy, remember, you've only observed an even smaller fraction of the reality right in front of you. Most of what constitutes your own body, your own immediate environment, operates at scales and in ways that are invisible to your direct experience. This isn't meant to be depressing. It's meant to be liberating. It means there are depths to reality, layers upon layers, that we're only beginning to explore. And you get to be part of that exploration, not just through science and telescopes, but through expanding your own consciousness, your own understanding, your own appreciation for the mystery we're embedded in. Now, let me take you to the edge of comprehension. We've talked about how the universe might extend far beyond what we can see. We've talked about multiverses, higher dimensions, holographic principles. But there's an even more dizzying possibility. What if there's no bottom? What if reality is an infinite regress, patterns within patterns within patterns, going down forever? Here's what I mean. We discovered that solid matter isn't really solid. It's made of atoms, mostly empty space. Then we discovered atoms are made of protons, neutrons, and electrons. Then we discovered protons and neutrons are made of quarks. And quarks might be made of vibrating strings of energy. But what if strings are made of something smaller? And that something is made of something smaller still? What if there's no fundamental layer, no ultimate building block where we can say, this is what everything is made of? Similarly, at the largest scales, we've talked about the observable universe, the larger universe beyond it, the multiverse. But what if that multiverse is itself part of something larger? What if universes cluster into metastructures, and those metastructures into megastructures with no top level? This is the concept of infinite regress, and it's both beautiful and terrifying. Beautiful because it means reality is infinitely rich, infinitely deep, endlessly fascinating. Terrifying because it means we can never truly understand everything. No matter how much we learn, there will always be deeper layers, larger structures, more complex patterns. Some versions of string theory and quantum gravity hint at this. They suggest that space and time themselves might not be fundamental. They might emerge from something deeper, perhaps a network of quantum relationships, perhaps patterns in a higher dimensional space we can't directly perceive. And what is that higher dimensional space made of? Perhaps it too emerges from something deeper. Still, if reality is an infinite regress, then asking, how much of the universe have we seen, is like asking, what percentage of infinity have you counted to? The question doesn't even make sense. We haven't seen any finite percentage of reality. We've seen an infinitely small fraction, which is functionally indistinguishable from nothing. But here's the beautiful part. That doesn't make our observations worthless. Every layer we understand, every pattern we discover, every mystery we solve, expands our consciousness, deepens our appreciation, and connects us more intimately with the infinite complexity we're embedded in. You don't have to understand everything to experience wonder. You don't have to see the whole universe to be amazed by the parts you can see. In fact, knowing that there's always more, that reality extends infinitely beyond your grasp, makes the mystery more profound, not less. I want to return to quantum mechanics for a moment, because there's something we need to address: the role of observation in creating reality. In the famous double-slit experiment, a particle behaves differently depending on whether we observe it. If you don't observe which slit it goes through, it acts like a wave, creating an interference pattern. If you do observe it, it acts like a particle, going through one slit or the other. The act of observation, of measurement, literally changes what happens. Before measurement, the particle exists in a superposition of states. Measurement collapses that superposition into a single, definite state. Now, this is usually explained at microscopic scales. But some interpretations of quantum mechanics, particularly the von Neumann-Wigner interpretation, suggest that consciousness itself plays a role in collapsing quantum wave functions. If that's true, then observers, conscious beings, aren't just passively observing the universe. We're actively participating in creating the definite reality we experience. Scale this up. Before conscious observers existed, did the universe exist in the same definite sense it does now? Or was it a vast quantum superposition of possibilities? The universe is about 13.8 billion years old. But Earth is only 4.5 billion years old, and life emerged perhaps 3.8 billion years ago. Complex life is even more recent. Conscious observers capable of understanding physics have existed for maybe a few 100,000 years. For most of cosmic history, minus 10 billion years, there were no conscious observers. No one to collapse quantum wave functions. No one to define what's real. Did the universe exist in the same way during those 10 billion years as it does now? Or was it in some sense less defined, less real, until observers evolved to experience it? This sounds like philosophy, but it's a genuine question in physics. Some versions of quantum mechanics, like the participatory anthropic principle proposed by physicist John Wheeler, suggest that observers are necessary for reality to be fully defined. The universe doesn't exist in a fully determinate way until it produces observers capable of observing it. Wheeler proposed a concept he called it from bit, the idea that physical reality, it, emerges from information, bit, and information only exists in relation to observers who can record and process it. If this is correct, then the question, how much of the universe have we observed, takes on a strange twist. The parts we haven't observed might not exist in the same definite sense as the parts we have observed. Our observations don't just reveal reality, they participate in creating the definite classical reality we experience. Think about that. You're not just a passive viewer of the cosmos. You're an active participant in bringing it into concrete existence. Your consciousness, your awareness, your active observation, these aren't separate from the universe. They're part of how the universe becomes real. Now let's talk about something that should disturb you: the silence. In 1950, physicist Enrico Fermi asked a simple question: where is everybody? The universe is vast. It's old. There are hundreds of billions of galaxies, each containing hundreds of billions of stars. Many of those stars have planets. Some of those planets are in the habitable zone where liquid water can exist. Even if life is rare, even if intelligent life is extraordinarily rare, the sheer number of opportunities means there should be millions of technological civilizations in our galaxy alone. Some of them should be far older than ours, civilizations with millions or billions of years of technological development. Where are they? Where are the radio signals, the megastructures, the signs of galactic engineering? Where are the probes exploring every star system? Where is the evidence of anyone else? This is the Fermi paradox, and it's one of the most unsettling questions in science. There are many proposed solutions. Maybe intelligent life is incredibly rare. Maybe civilizations tend to destroy themselves shortly after developing technology. Maybe there's some great filter, a challenge so difficult that almost no civilization survive it, and we either haven't reached it yet, or we've somehow passed it. But here's a possibility that relates to everything we've discussed. Maybe the parts of the universe that are observable to us are empty, because the interesting stuff, the life, the civilizations, the complexity, exists in parts of the universe we can't see. Maybe life requires specific conditions that only exist in certain regions of the cosmos, regions beyond our cosmic horizon. Maybe the observable universe, for all its vast size, happens to fall into a dead zone where the physical constants or environmental conditions aren't quite right for widespread life. Or maybe, and this is even stranger, advanced civilizations have found ways to leave the observable universe. Perhaps sufficiently advanced technology allows beings to access higher dimensions, parallel universes, or other structures in the multiverse. Maybe the endpoint of civilization isn't expanding throughout the galaxy, but transcending into realms we can't detect or imagine. If that's true, then the universe we observe isn't just materially incomplete, it's evolutionarily incomplete. We're seeing the starting zone, the nursery, the region where civilizations begin. But where they go when they mature, where they ultimately exist, is beyond our ability to observe. The silence of the cosmos might be telling us something profound, that the universe we can see is just the shallow end of a much deeper pool. And the depths, where the truly interesting things happen, are invisible to us. Everything I've told you so far has been about what we can't see in space. But there's also something we can't see in time. Let me tell you about the end of the universe, and why even that might not be the end. According to our current understanding of cosmology, the universe's ultimate fate is something called heat death. As the universe continues to expand, driven by dark energy, galaxies will drift apart. Eventually, all the stars will burn out. Black holes will be the last massive objects remaining, and even they will evaporate through Hawking radiation over incomprehensibly long timescales, YHA years or more. Finally, the universe will reach a state of maximum entropy, complete disorder, where no energy gradients exist, no work can be done, and nothing interesting can happen. It will be cold, dark, and dead forever. That's the conventional picture. But physicist Roger Penrose has proposed something called conformal cyclic cosmology that completely reframes this ending. Penrose suggests that after heat death, after all matter has decayed and only massless particles remain, something strange happens. In a universe with no massive particles, there's no way to define scale. There's no reference frame, no way to measure time or distance. In such a universe, infinity and zero become equivalent. The end of our universe, after infinite expansion, infinite time, maximum entropy, becomes identical to the beginning of a new universe. The Big Bang of the next cosmic cycle emerges from the heat death of the previous one. Under this model, what we call the observable universe isn't just limited in space, it's limited in time. Our cosmic history might be one chapter in an infinite book, with previous chapters we can't access and future chapters not yet written. We've observed 13.8 billion years of cosmic history. But how much cosmic time has actually elapsed? If the universe is cyclic, it might be infinite. We might be living in the trillion cycle with no way to know what came before. And here's what should really blow your mind. If each cycle can have different physical constants, then the universes before ours might have had completely different physics. Different particles, different forces, different structures. And the universes after ours will be different again. We're observing one frame of an infinite movie, and each frame is a different universe with different laws. How much of reality have we seen? One moment in an eternal cycle. One set of physical laws in an infinite progression of different laws. One note in an endless symphony. Before I continue, I need to ask you something. We're 100 minutes into this journey, and if you've made it this far, you're exactly the kind of curious, open-minded person who needs to share this knowledge. Hit that subscribe button if you haven't already, and share this video. Drop a comment telling me, how has this changed your perspective? What are you thinking about differently now? I genuinely want to know, because we're about to go even deeper into territory that will challenge everything you think you understand about existence. I want to explore something that's going to sound insane at first, but bear with me. What if consciousness isn't just something that happens in brains? What if it's a fundamental property of the universe, like gravity or electromagnetism? This idea is called panpsychism, and it's been explored by philosophers for centuries. But recently, some physicists and neuroscientists have started taking it seriously. Here's the argument. Consciousness is the one thing we know with absolute certainty exists. Descartes said, "I think, therefore I am." Our own consciousness is the only thing we can't doubt. Everything else, the external world, other people, physical laws, could theoretically be an illusion. But the fact that we're experiencing something is undeniable. Yet consciousness is deeply weird. We have no physical explanation for how subjective experience arises from brain activity. We can map neural correlates of consciousness, brain regions that activate when you're conscious versus unconscious. But correlation isn't explanation. We can't explain why there's something it's like to be you, why your neurons firing creates first-person experience. This is called the hard problem of consciousness, and it's stumped philosophers and neuroscientists for centuries. Some researchers, like Giulio Tononi and Christoph Koch, have proposed that consciousness might be a fundamental property of information integration. According to integrated information theory, any system that integrates information, any system where the whole is more than the sum of its parts, has some degree of consciousness. Your brain has a massive amount of integrated information, so it has rich, complex consciousness. A thermostat has a tiny amount, so it has the tiniest whisper of experience. Even atoms might have some infinitesimal proto-consciousness. If this is true, then consciousness isn't something that occasionally emerges in special places like brains. It's woven into the fabric of reality itself. The universe isn't just observed by conscious beings. It's made of consciousness at every scale. Now connect this to quantum mechanics. Remember how observation seems to collapse quantum wave functions? What if that's because consciousness is fundamental to how reality works? What if the physical universe, space, time, matter, energy, is actually an expression of cosmic consciousness observing itself? I know this sounds like mysticism, but there are serious physicists exploring these ideas. Max Tegmark at MIT has proposed that consciousness is a particular kind of information processing that emerges from quantum states in the brain. Others, like Donald Hoffman, suggest that space-time itself is a user interface created by consciousness, rather than consciousness emerging from space-time. If consciousness is fundamental, then asking, how much of the universe have we observed? Is asking, how much of universal consciousness has become self-aware through observers like us? And the answer might be, almost none. There might be levels of consciousness, forms of awareness, modes of experience existing throughout the cosmos that are as far beyond human consciousness as human consciousness is beyond a thermostat. We might be tiny sparks of awareness in an infinitely vast field of consciousness, glimpsing only the smallest fraction of the total experience embedded in reality. Let's shift gears and talk about something that might seem unrelated at first, but connects to everything: mathematics. Here's a strange fact. Mathematics is unreasonably effective at describing the universe. When physicists want to understand how nature works, they write equations. And these equations, abstract mathematical relationships that humans discovered in their minds, turn out to perfectly predict what happens in the real world. Why should this be? Why should the universe obey mathematical laws at all? Why shouldn't it be chaotic, arbitrary, random. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. He couldn't explain why abstract math, developed in the human mind, corresponds so precisely to physical reality. There are two possible answers, and both are mind-bending. Option 1. The universe is fundamentally mathematical. Physical reality isn't described by math. It is math. Particles, fields, forces, space-time, these are all mathematical structures. What we call physical existence is actually patterns and relationships in an abstract mathematical space. This is the mathematical universe hypothesis, proposed by Max Tegmark. In this view, every mathematically consistent structure exists somewhere in a vast mathematical multiverse. Our universe is one such structure, a particular set of equations, a specific mathematical pattern. But there are infinitely many other mathematical structures, and they all exist with equal reality. There are universes where 2, 2 equals 5, operating under different mathematical axioms, universes with different geometries, different dimensions, different rules. We observe the particular mathematical structure we do because it's complex enough to support observers. But we're just one pattern in an infinite library of mathematical possibilities. Option 2. Mathematics is a language of consciousness. It's the way conscious minds understand reality. The universe doesn't obey mathematical laws. Rather, consciousness imposes mathematical structure on the cosmos as it observes and understands it. In this view, the universe before consciousness is more like a quantum superposition, undefined, potential rather than actual. Consciousness brings mathematics into the picture, and through mathematics, brings definite reality into existence. Both options have radical implications for how much of reality we've observed. If option 1 is true, we've observed one mathematical structure among infinitely many. The universe we see is just one solution to one set of equations in an infinite space of mathematical possibilities. If option 2 is true, we've observed the part of reality our consciousness has mathematically structured and understood. The rest, the pre-conscious, pre-mathematical reality, is literally beyond observation, because observation requires imposing mathematical structure. Either way, the observable universe isn't the totality of what exists. It's a tiny slice, one pattern, one structure, one mode of existence, in something vastly larger and stranger. Now I want to completely mess with your understanding of time, because there's a sense in which everything past, present, and future already exists, and we've only observed an infinitesimal slice of it. In relativity, time is a dimension, just like the 3 dimensions of space. Einstein showed that space and time are woven together into spacetime, a 4-dimensional structure where past, present, and future all exist simultaneously. Think about it this way. Imagine a book. Every page exists, right? The last page exists just as much as the first page. When you're reading page 50, page 100 already exists. You just haven't experienced it yet. You're moving through the book sequentially, but the book itself is a complete static object. Einstein's relativity suggests the universe is like that book. All moments of time, past, present, future, exist together in a 4-dimensional spacetime. You experience time as flowing because your consciousness moves through it, moment by moment. But from a 4-dimensional perspective, your entire life, from birth to death, exists as a single, complete object. This is called the block universe view, and it's a mainstream interpretation of relativity. Your past self exists right now in the past region of spacetime. Your future self exists right now in the future region. You just can't perceive them simultaneously because your consciousness is constrained to experience one moment at a time. Now here's what this means for how much of the universe we've observed. We haven't just failed to observe distant regions of space. We've failed to observe most of time. You've experienced maybe 30, 40, 70 years of time. But the universe contains 13.8 billion years of past time. And if the universe continues for trillions or quadrillions of years into the future, you'll have experienced a vanishingly small slice of the temporal dimension. Imagine the entire timeline of the universe laid out as a line. Your life, your entire experience of time, is a dot on that line, a single point. You've observed one moment in a vast temporal landscape that extends billions of years into the past and potentially infinitely into the future. And it gets weirder. Relativity also tells us that time passes at different rates depending on your motion and gravitational field. Clocks on satellites tick faster than clocks on Earth. Time near a black hole passes slower than time in empty space. This means now isn't universal. There's no cosmic present moment that everyone agrees on. Two observers in different locations, moving at different speeds, will disagree about what events are happening now versus in the past or in the future. The universe doesn't have a single timeline. It has countless overlapping timelines, each one equally valid, depending on your reference frame. How much of time have we observed? From our reference frame, we've observed a tiny slice. But from other reference frames, from the perspective of particles moving near light speed or existing near black holes, time has passed differently. There are temporal regions, temporal experiences, that exist but are inaccessible to us because of our particular motion through spacetime. Let's stay with time for a moment, because the future represents an entire category of unobserved universe that we haven't talked much about. We can observe the past. We have fossils, geological records, light from distant stars that's been traveling for billions of years. The cosmic microwave background lets us see the universe as it was 380,000 years after the Big Bang. The past is, in some sense, accessible, but the future? Completely invisible. We can predict, extrapolate, calculate probabilities, but we cannot observe it. We cannot know it with certainty. Now, in a deterministic universe, a universe where everything that happens is completely determined by what came before, the future exists in potential. It's already locked in by the laws of physics and initial conditions. We just don't know what it is yet. But quantum mechanics suggests the universe isn't deterministic. At the quantum level, events are probabilistic. An electron can be in a superposition of locations until measured. A radioactive atom exists in a superposition of decayed and not decayed until observed. This means the future literally doesn't exist yet, not even in potential. It's genuinely open, undefined, waiting to be collapsed into actuality by the ongoing process of quantum measurement and observation. Think about what this means. There's an entire dimension of reality, the temporal dimension, extending into the future, that is fundamentally unobservable until it becomes the present. And once it becomes the present, it immediately becomes the past, accessible only as memory and evidence. You exist at the leading edge of creation, the boundary where undefined future becomes definite present and then fixed past. You're surfing on the crest of a wave where reality is being continuously created. How much of the universe have we observed? We've observed 0% of the future, none of it. No matter how sophisticated our predictions, no matter how good our scientific models, the future remains utterly invisible until it arrives. And given that the universe might continue for trillions of years, or might be eternal, the amount of unobserved future vastly exceeds the 13.8 billion years of past we can study. We exist in a tiny present moment, sandwiched between an increasingly distant past and an infinitely large, utterly unknown future. Almost all of temporal reality is inaccessible to us, either because it's already gone or because it hasn't happened yet. Now let's talk about something hopeful. How our ability to observe the universe is rapidly expanding, and what that tells us about the relationship between consciousness, technology, and reality. 1,000 years ago, humans could only see what their naked eyes revealed, a few thousand stars, the Milky Way as a cloudy band across the sky, 5 planets besides Earth. That was the entire known universe. Then Galileo pointed a telescope at the sky and discovered Jupiter's moons, Saturn's rings, countless more stars. The observable universe expanded. With better telescopes, we discovered galaxies beyond our own. Then we discovered the universe was expanding. Then we found the cosmic microwave background. Each new technology revealed layers of reality that had always existed but were invisible to us. In the 20th century, we started observing in wavelengths beyond visible light. Radio telescopes revealed pulsars and quasars. X-ray telescopes showed us black holes. Infrared telescopes let us see through dust clouds to witness star formation. Each new window on the electromagnetic spectrum revealed phenomena we never knew existed. And now we're observing with things that aren't light at all. Gravitational wave detectors let us hear colliding black holes. Neutrino detectors let us see inside the cores of stars. We're building quantum sensors that might detect dark matter directly. Each new instrument expands the observable universe. Things that were invisible become visible. Mysteries become data. Here's what's profound about this. The universe hasn't changed. Dark matter was always there. Gravitational waves were always rippling through space. Black holes were always colliding. But until we built the tools to observe them, they were, for us, non-existent. This suggests something deep. The boundary between observed and unobserved isn't fixed. It's determined by the sophistication of our observation. As consciousness develops more advanced tools, more of reality becomes accessible. And there's no reason to think we've hit a limit. Right now, we're building quantum computers that might simulate universes in ways that reveal new physics. We're planning gravitational wave detectors in space that will be millions of times more sensitive than current ones. We're designing neutrino telescopes that could observe the cosmic neutrino background from 1 second after the Big Bang. We're even talking about building telescopes on the far side of the moon, or in the outer solar system, or eventually in orbit around other stars. Each new vantage point will reveal structures and phenomena currently hidden from us. In principle, there might be no hard limit to what consciousness can observe, given enough time and technological development. The 5% of the universe we've seen might grow to 10%, then 20%, then more. But here's the catch. Even as we expand our observational capabilities, the universe itself is expanding and evolving. New structures are forming. Cosmic horizons are shifting. We're chasing a moving target. We might never catch up, never observe everything, even if we have infinite time. The pursuit of knowledge is infinite. Every answer spawns new questions. Every discovery reveals deeper mysteries. The observable universe expands, but so does our awareness of how much remains unobserved. Let me get philosophical for a moment, because I want you to understand something fundamental about what observation even means. When we say we've observed something, what do we really mean? We mean that information from that thing has reached us in some form. Photons, gravitational waves, neutrinos, whatever. And we've recorded and interpreted that information. But information takes time to travel. When you observe a star 100 light years away, you're not observing it as it exists now. You're observing it as it existed 100 years ago. The light you're seeing left that star a century ago. The star might have exploded last year, but you won't know for another 99 years. When we observe the Andromeda Galaxy, 2.5 million light years away, we're seeing it as it was 2.5 million years ago. When we observe the cosmic microwave background, we're seeing the universe as it was 13.8 billion years ago. We're always observing the past, never the present. The further we look, the deeper into history we see. This means the observable universe isn't a snapshot of how the universe currently is. It's a patchwork of different eras. Nearby objects we see as they were recently. Distant objects we see as they were billions of years ago. It's like if you could only see people by receiving letters from them, and the letters took years to arrive. Your friend across the street sends a letter that arrives tomorrow. telling you what they're doing today. But your friend in another country sends a letter that takes years to arrive, telling you what they did years ago. You never see anyone as they currently are. You see a collection of messages from different times, and you have to mentally reconstruct what everyone must be doing now based on outdated information. That's what cosmology is. We're reconstructing the current state of the universe based on ancient messages, light and other signals that took billions of years to reach us. And here's the disturbing part. We can never know what's happening right now in distant parts of the universe. By the time information reaches us, it's old news. The distant galaxies we see might have long since been destroyed. The cosmic structures we observe might have completely evolved into something different. There's a sense in which the current state of the universe is fundamentally unknowable. We can only know the past. And the further away something is, the more ancient the past we're observing. How much of the universe have we observed? We've observed the past states of a tiny region around us. But the present state of the universe, what everything is actually doing right now, is almost completely hidden from us, veiled behind the time delay of light. Now, I want to take you somewhere even stranger. We've talked about how much of the physical universe we haven't observed. But what about other minds, other consciousnesses? You have direct access to exactly one consciousness, your own. You know what it's like to be you. You experience your thoughts, your feelings, your sensations from the inside. But everyone else, you infer they're conscious. You see them behave in ways similar to how you behave. You assume they have inner experiences similar to yours. But you can never directly experience someone else's consciousness. You can never know what it's like to be them. This is called the problem of other minds, and it's one of the oldest puzzles in philosophy. Now, most of us assume other humans are conscious. The evidence seems overwhelming. But what about animals? A dog seems conscious in some way, but is its experience similar to ours? What about an octopus, whose nervous system is organized completely differently? What about an ant or a bacterium? And what about potential non-biological consciousness? If we create artificial intelligence sophisticated enough, will it be conscious? Would it have subjective experiences, or just simulate them? How would we know? Here's why this matters for our discussion. Consciousness might be far more widespread in the universe than we realize. If panpsychism is true, if consciousness is a fundamental property of information integration, then consciousness exists everywhere, in stars, in planets, in clouds of gas, in black holes. These wouldn't be human-like consciousnesses. They wouldn't think thoughts or have human emotions. But they might have their own forms of experience, their own ways of being something. And we've never observed these consciousnesses. We can't. Consciousness is, by definition, subjective, knowable only from the inside. You can observe a brain and its activity from the outside, but you can never directly access the experience that brain is generating. This means there might be an entire dimension of reality, the dimension of subjective experience, of consciousness, that is fundamentally unobservable except from within. The universe might be teeming with minds, with experiences, with forms of awareness we can't detect or imagine. Every star might have some form of experience. Every galaxy might possess a vast, slow, alien consciousness. The universe itself might be conscious in some incomprehensible way, and we'll never observe these consciousnesses directly. We'll only observe their external behaviors, their physical correlates. The inner experience, the what it's like to be a star or a galaxy or the universe, is forever inaccessible. How much of reality have we observed? We've observed physical structures and processes, but we've only directly experienced one consciousness, our own. The vast space of possible experiences, the infinite varieties of awareness that might exist throughout the cosmos, is almost entirely unobserved. I want to tell you about something that's going to break your brain. Gödel's incompleteness theorem. It's a mathematical proof, but its implications extend far beyond mathematics. It tells us something profound about the limits of knowledge itself. In 1931, logician Kurt Gödel proved that in any mathematical system complex enough to include basic arithmetic, there are true statements that cannot be proven within that system. You can add more axioms, expand your system, but you'll always create new unprovable truths. Mathematics is fundamentally incomplete. Now, here's why this matters. If the universe is mathematical, if physical reality is a mathematical structure, then Gödel's theorem might apply to the universe itself. This would mean there are true facts about the universe that can never be proven or derived from physical laws. Not because we're not clever enough, or because our instruments aren't good enough, but because proof is impossible in principle. Physicist Stephen Hawking, before his death, argued that Gödel's theorem might place fundamental limits on our ability to understand the cosmos. There might be a theory of everything, a complete set of physical laws, but we might never be able to prove it's correct or complete. There will always be phenomena that these laws can't fully explain or predict. Think about what this means. No matter how much we observe, no matter how sophisticated our theories become, there will always be aspects of reality that remain mysterious. Not mysterious in the sense of we haven't figured it out yet, but mysterious in the sense of it's impossible to figure out with logical reasoning. The universe might contain truths that can only be known through direct experience, never through derivation or proof. It might contain paradoxes, self-referential structures, and logical impossibilities that somehow exist anyway. This isn't mysticism. This is mathematics telling us that knowledge has intrinsic limits. That reality might be fundamentally inexhaustible. That consciousness and observation can never capture everything, because everything includes things that transcend the very system of logic we use to understand. How much of the universe can we observe? Gödel's theorem suggests never all of it. There will always be true facts about reality that are unobservable, unprovable, unknowable through the methods of science and logic. The project of understanding the universe is not just practically infinite, it's logically impossible to complete. Let's bring this back to you, to your life, to how you should think about yourself in light of everything we've discussed. We've established that the universe is vastly larger, stranger, and more complex than anything you could observe or understand. Most of reality is hidden from you, not just beyond your cosmic horizon, but beyond the reach of your senses, your instruments, your concepts, your logic. This could be depressing. It could make you feel small, insignificant, powerless. What's the point of trying to understand anything if most of reality is forever beyond your grasp? But I want to offer you a different perspective. This should be liberating, thrilling. It means you live in an inexhaustible universe. No matter how much you learn, there's always more. No matter how deeply you understand, there are deeper levels. Reality will never become boring, never become fully known, never stop surprising you. You're like a child on a beach, playing with pebbles and shells, while an entire ocean stretches before you. An ocean so vast that you could explore for infinite lifetimes and never see it all. And that's beautiful. That's something to celebrate. Think about it. If we lived in a small, simple, fully understood universe, existence would be claustrophobic, finite. There would be a point where we'd learned everything worth learning, discovered everything worth discovering. We'd reach the boundary of knowledge and have nowhere else to go. But we don't live in that universe. We live in something infinitely richer. Every time we think we've found the edge, we discover there's more beyond it. Every mystery we solve opens up new mysteries. You personally get to participate in this cosmic exploration, not just through science, but through your own consciousness, your own experience, your own unique perspective on reality. You are a unique observational vantage point. No one else sees the universe exactly as you do. No one else has your combination of experiences, thoughts, insights. You're adding something to the universe's self-knowledge that has never existed before and will never exist again. And when you die, your particular window on reality will close. The universe will lose your perspective forever. In that sense, your observations, however limited, however small, are precious. They're irreplaceable. The universe needs observers. Without consciousness, all of this, the galaxies, the quantum fields, the mathematical structures, would exist in some abstract sense, but there would be no one to appreciate it, to experience it, to marvel at it. You're the universe's way of appreciating itself. And that's not a small role. That's a profound responsibility and privilege. Let me introduce you to a concept: finite versus infinite games. Philosopher James Carse wrote about this, the idea that there are two kinds of games in life. Finite games are played to win. They have defined rules, boundaries, endpoints. Football is a finite game. Chess is a finite game. You play to achieve a specific goal, and when that goal is reached, the game ends. Infinite games are played to continue the game. The purpose isn't to win, but to keep playing. To expand the game, invite more players, discover new rules. The goal is perpetuation, not conclusion. Understanding the universe is an infinite game. We're not trying to reach some final endpoint where we know everything and can stop. We're trying to sustain and expand the process of discovery itself. Every observation we make, every mystery we solve, opens up new territory to explore. Every answer generates new questions. The game expands as we play it. And unlike finite games, infinite games are non-competitive. We're not competing against each other to see who can understand the universe first. We're collaborating across time and space, building on the observations of people who lived centuries ago, creating knowledge that people centuries from now will build upon. You're part of an infinite lineage of observers. The astronomers of ancient Babylon who first mapped the stars, Galileo with his telescope, Edwin Hubble discovering the expansion of the universe, Vera Rubin revealing dark matter, the scientists right now analyzing data from the James Webb Space Telescope, and you, watching this video, thinking about these ideas, adding your consciousness to the collective human project of understanding reality. When we ask, how much of the universe have we observed? Or asking a finite game question, we're trying to quantify, to measure progress towards some imaginary endpoint. But if we shift to an infinite game perspective, the question becomes, how can we expand our capacity to observe? How can we invite more minds into the process of discovery? How can we sustain and enrich the game of cosmic exploration? The answer isn't we've observed 5%. The answer is, we're constantly expanding what's observable, and that expansion has no limit. The universe isn't something to be conquered or completed. It's something to be engaged with forever. Now I want to address something that might be bothering you. With all this talk about how vast and unknowable the universe is, you might be wondering, what's the point? If we're so tiny, so limited, so unable to grasp the whole picture, does anything we do matter? This is the question of meaning, and it's crucial. Here's what I believe. Meaning isn't something you discover out there in the universe. It's something that emerges from the relationship between consciousness and reality. The universe, in itself, is neither meaningful nor meaningless. It's just structure, process, relationship. Quantum fields fluctuating, space expanding, matter clumping into stars and galaxies. None of that has inherent meaning. It just is. But when consciousness arises, when the universe starts observing itself through evolved minds, meaning emerges. Meaning is what happens when awareness encounters reality and cares about what it finds. You care that the universe is beautiful. You care that it's mysterious. You care that there are things to discover. You care about the people in your life, the projects you work on, the experiences you have. That caring, that mattering, is where meaning lives. Not in the cosmos itself, but in the relationship between your consciousness and the cosmos. And here's the beautiful part. Your meaning-making contributes to the universe. The universe without consciousness is just vast, cold mechanics. But the universe with consciousness, with beings who observe it, understand it, appreciate it, create meaning from it, is something richer. You're not a passive observer of a meaningful universe. You're an active creator of meaning within the universe. When you look up at the night sky and feel awe, you're adding something to reality that wasn't there before. When you think deeply about these mysteries, you're participating in the universe's process of understanding itself. When you create art, love other people, pursue knowledge, or simply experience the texture of a moment, you're contributing to the total richness of what exists. The fact that the universe is vast beyond comprehension doesn't diminish your significance. It amplifies it. You're a rare, precious pocket of consciousness in an otherwise unconscious cosmos. You're one of the universe's few ways of experiencing beauty, wonder, and meaning. How much of the universe matters? All of it matters, but only because there are beings like you who can care that it exists. Let me tell you about something philosophers call the observer's paradox, because it captures something profound about our situation. The paradox is this: we can only observe the universe from inside the universe. We're not external observers looking at reality from outside. We're part of what we're trying to observe. It's like trying to see your own face without a mirror, or trying to observe your brain while it's observing. The instrument of observation is embedded in what's being observed. This creates fundamental limitations. When physicists try to understand the quantum vacuum, the empty space that's actually seething with virtual particles, they're using instruments made of matter that emerged from that vacuum. They're using brains evolved within this universe to understand the universe itself.